So let's say we have this kind of truss bridge, right? And those of you who are from the civil engineering probably will appreciate a lot. So we have a truss bridge like this. And we can see that on one end we have a pin joint, we have a roller. So this is a whole thing is a simply supported structure. And there's some weight of this truss, right? So what's the free body diagram of this? How do you draw a free body diagram of the whole truss? It's really very simple. All you have to do is draw this bridge without any support shown, without any ground. We know that point A, you can have reaction forces along X and Y direction. And at point B, you can only have reaction in the vertical direction. That's the normal and the weight. And then you show your coordinate system. That's it. That's your free body diagram, right, for the truss bridge. Okay, another example. So in this case, we have an object that is supported on a platform, on a plank, right, and there's a cable. Right. First question, what kind of support do you think you have between this wall and the platform at point A? Is it a cantilever? It's a pin joint, right? It cannot be a cantilever because you need to allow rotation about this point, right? So this is a pin joint. So if it is a pin joint, then if you want to draw the free body diagram of the platform, you only have the reaction forces, which are X and Y, AX and AY. You have this cable. Cables can only exert forces in the longitudinal direction, so that's a tension force, so we show that. We have the weight of the platform, and we have the normal reaction from the object on the platform, right? We're calling it N sub C, and that's the free body diagram. Okay, so this is a problem from your textbook, right? This is problem 3.9. It says that you have three forces, a force of 100 pound at 60 degree from x-axis, 200 pound along vertical direction, and a force P of unknown magnitude acting at 40 degree from x direction downward way. The question is, given all these three forces, what should be the magnitude of P so that the resultant is as small as possible? So we are looking for resultant of these three forces, right? So let's call this force as F1, this as F2, and we'll call this as F3, right? So what is the resultant? Let me write it algebraically first. Sigma F is force F1 plus force F2 plus force F3, right? Okay, so the question is, if I write these forces, let's say F1 is 100 cosine 60 I hat plus sine 60 j hat, and F2 is 200 entirely along positive j hat direction, and F3 is P cosine 40 I hat minus sine 40 j hat. Then the question is, what should the magnitude of P be? What should P be such that norm of sigma F is minimum? That's the question, right? So what should that P be so that the resultant is as small as possible? So what do you think? Can you answer that question? How do we answer that question? What should P be? 0? So P should be 0? Anybody else? Well, it turns out that P being 0 will not give you the lowest resultant, because these are not scalar quantities. These are vector quantities, right? With the vector quantities, direction is also important. So you have to worry about that as well. So there are two ways you can solve this problem. One is, if you are, if you're good with calculus, right, you could write this algebraic equation. We just wrote this, and you could compute the norm of sigma F. You could compute the norm magnitude of the sigma F, right? And this will be a function of P, right? Because you have X component, you have the Y component, and you write the magnitude, which will be square root of, fx squared plus fy squared. Then you have this function, which is in terms of variable P. You take the derivative with respect to P, equate it to 0, right? And then you solve for P from that. And that'll be a very mathematical way of solving the problem. What are you guys so happy about? Yes, please share the news with us. Back there. But you understand that you are in this class and you are disturbing your fellow classmates, right, by doing that. I understand. That's good, which means you're not paying attention here. So you're losing on this. You're gaining on something else, I guess, over there. But is this the best time to do that? And your classmate sitting right next to you, he probably has no idea what you're thinking. Okay, so you can take the derivative and write the equation to be equal to 0, and you can solve for p, right? But I know that most of you in this class are probably not at that level, right, in terms of calculus. You will be there maybe in a semester or two. So how do we solve this problem, right, at the level we are at right now? It's easy. So what we are going to do is we are going to take a graphical approach, sort of a semi-graphical approach. So we have f1, we have f2, and we have p over here, right? We know p is pointing at 40 degrees below x-axis. Let's try to draw all of them in a vector polygon and see what we can do with it. So I'm going to draw this again. So let me erase this because we don't need this. This is not how you'll be solving the problem, right? So I have I hat over here. I have j hat over here. Okay. I'm first going to draw f1, right? So that's 100 pound. So this is 60 degree. And I'm not really actually, using a scale like 1 centimeter equal to 10 pound and doing something like that, right? I'm just showing you the sketch. So this is f1. Then I have 200 pound, which is basically a force that is going this way. You know what? Let me first draw f2. That'll be easier to understand. Sorry about this. Let me first draw f2 because f2 is already this way. So we have f2 right over here. That's f2. Then I'm going to draw f1, which is right here. This is 60 degree. Okay, this is f1. And then I have p. P is at 40 degree right here. This is 40 degree. That's p. Okay, so what is the resultant? Resultant would be, depending on what the length of p is, which we don't know, this will be the resultant. Let's call it r. Right? But we don't know what this length is. If this length is here, then that would be the resultant. If this length is here, then this would be the resultant. So when do we have the lowest length, smallest length for r? When do we have the smallest length for r? We have the smallest length when this is perpendicular to this line, right? Any other resultant, either above or below it, is going to be more, right? So the lowest resultant you can get is by drawing the perpendicular to this line of action of p, and that's the r. Now it's easy. You have this perpendicular over here. All you have to do is use a little bit of trigonometry, and you'll figure out what that r is. So what would p be? P would be this length. That's it. Does this make sense? Yes? Right? So you see, so if p is equal to 0, you would get this as the resultant, which is clearly more than this. So if this is r1, this is r2, this is r3, this is r4, then r1 is clearly more than r2. Right? R3 is clearly more than R2. R4 is clearly more than R2. So the lowest possible length that you can get for the resultant is when that resultant vector is actually perpendicular to the line of action of P. Okay?